Okay, ladies and gentlemen, we are doing another GES1 from 2020, December 2020. And yep, GES1, and we're going to start on section 8. Let's have a look at the first part. A bit of algebra. Simplify each of the following and rearrange to make x the subject of the expression. Oh yeah, this one again, no problem. So let's start with A. We'll see if we can fit it in here. Y is equal to bx cubed over x squared times by x to the 4 over 4b. Now, one thing I would suggest we do is we simplify before we multiply, but this one's really easy. It doesn't really matter how you do it. There's a couple of different ways you can do it. So I'm just going to multiply these guys together on the top, which means I'm going to add their powers. This is going to end up being b x to the 7. And then the same thing on the base, we're going to get x squared for b. I can just slide them together. Everything's multiplied here. Literally everything's multiplied. This is multiplied by that. This is multiplied because you can see that multiplication is symbol in the middle, but 4 times by b is like that anyway. We can just take away the multiplication. We don't need to write it. That makes life really easy. The b's are going to cancel, which is really nice. This x to the 7 over x squared, that's going to cancel as well. We're just going to get x to the 5 because we can cancel out these with the top over 4. I can do that in a little bit more detail to explain why this stuff cancels, but it's pretty simple stuff. I mean, you just minus it off. If they're multiplied, you add the powers. If they divide, you minus the powers. And you see I could have simplified it here to start with, but whatever. We got the answer. It's done. Let's go to the next one. Part B. Oh, wait a second. Am I done? Let's read the question. Simplify each of the following to rearrange x to make it the subject. So I'm not done because I have to do a little tweak on this. What I've got now is y is equal to x to the 5 over 4. I need to make x the subject, which means it has to be x is equal to something. First thing I'm going to do is multiply both sides by 4. So I get 4y is equal to x to the 5. That's great. And then I can cube root both sides. It's going to look like this. I mean, fifth root both sides. Wow, let's put a fifth root up there. Let's just move that up so you can see a bit clearer. I know the YouTube search bar might mess it up a bit. Can I put it about here? Okay. So this and this are going to cancel out. And then we've got what we're looking for. Now we've just got the fifth root of 4y is equal to x. That's actually the answer. That's what we need. We can write it forwards or backwards. It's fine. It's really good. Now we're going to do part B. Let's see if we can grab part B and put it up here. We've got y is equal to x squared times by z cubed. There's no point putting the multiplication in there. It's fine. Divided by z squared. Divided by double division. That's always fun. 2x to the 5 z over x squared. I'm going to move this across so I can work on it better. So this is what we're calculating. Again, I got two different things I can do. I can flip it straight away. It depends on how comfortable you are with this. I can flip it straight away, or I can just cancel stuff out and then flip it. It doesn't really matter. We could do it both ways. We could try cancelling this out. I would cancel it out personally. The z to the 3 and z to the 2 are definitely going to cancel out. I'm just going to leave me with just one z like that. I can cross it out like that. It's like saying 3 minus 2. We're going to end up with x squared z. That's all it's going to be. I can write it over 1 if you like it like that. That'll be fine as well. Let's write it like that. Then these x's are going to cancel because I've got x's on top, x's on the bottom. This 5 and this 2, what's 5 minus 2 is going to be equal to 3. So let's rewrite that a little bit neater because it's a bit of a mess. We're going to get 2x3 to the power of 3 over times by z over 1 as well. Now I can flip this if really, really need to. It's basically what's going to happen is this is going to go down there anyway. I don't even need to write it. I could just write like this, right? But let's do it like this. I understand it's been a while since you guys have studied mathematics like this. So let's do keep, flip, change. I'm going to keep the first one exactly the same. It's going to be x squared z over 1. I'm going to flip the second one so it becomes, this is going to flip. So it's going to become 1 and 2x cubed z. And then I'm going to change this division into a multiplication because who knows how to do division with fractions anyway. Let me move my KFC, totally not copyrighted, to the other side. It means keep, flip, change. Right, then I'm going to slide these things on top of each other, because when you multiply fractions, you multiply the tops, you multiply the bottoms, you multiply this by 1, you just get the same thing. We're going to get x squared z over 2x cubed z. That's good. Anything I see on top, I can cancel out with something on the bottom, if it's on tops and bottoms, so these z's are going to go. Now this x squared and x to the cubed, let's explain this a little bit. X squared means x times by x. This dot means multiplication. And on the bottom, it's going to be 2x times 2x times by 2x, like that. Just so you can see it a little bit better. Anytime I have an x on top, I can cancel out with an x on the bottom. We cancel out this one as well. We're all cancelled out. But what do I leave on top here? Oh, sorry. What do I leave on top here? It will just be a 1 over 2x. Whew, okay, we got there, but we're not done yet, because remember we have to make x the subject of this, so we can pull this all together. We now have y is equal to 1 over 2x. We need to get to work on just this by itself. This needs to be moved so the x hat can be moved up. We can transpose this, we can rearrange it. How we rearrange it is we're going to multiply both sides by x, like this. That cancels out this x, and just moves it to the other side. So now I've got xy is equal to a half. And then I'm going to divide through by y, like this. Dividing through by y means y would actually go down to here on the bottom. Cancel that out. And now I've done it. I'm going to have x is equal to 1 over 2y. Okay, that's actually the answer we're looking for, because it said make x the subject. It might not be the easiest way for you to do it, but it's a different way. And I'm going to show you in every video like a different way to do it. We're going to see lots of repetition, because I've got there's about three different techniques to do this. And sometimes it helps you to see it another way. So that's it. We got it. Okay, question number 2. This is it's a really hard one. It's a lot of work involved. A lifeboat davit has a straight arm pivoting about P at deck level as shown in the picture. When launching the lifeboat, the davit arm makes an angle of 10 degrees to the deck. So what's going to happen is they're going to drop this boat into the water. I mean, this could be the arm, right? And then the arm's going to come round as it drops down, and hopefully the boat is not going to hit the ship's side. It's going to be dropped into the water, no problem. Determine the required length for the davit arm, so the clearance of 0.8 between the ship's sides and the lifeboat when launching, or at launching. So there's a lot of stuff going on here. Like I said, we've got to get our head around the problem first of all. Let's see if we're going to draw it when it's dropped down in this position. What's going to happen? This thing's like what? Is it like a semicircle? Not really. Is it like a triangle? I suppose. So let's see if we can just draw it first of all. Let's see what's going to happen. I know the length from the base. They tell me it's going to be at 10 degrees. 10 degrees here. And then the boat's going to be hanging off the end like this. I mean, it's a really fun one to do, but it's a really hard one to do. Alright. I don't think many people are going to be able to do this. Oh, that's really far out. I wanted to make this really close, right? Because we've only got 0.8 meters. So I think it should look a bit more like this. That's better. All right, we know that the lifeboat is 2 meters across. This is 2 meters right here. Might want to draw it a little bit bigger. It's pretty small, huh? 2 meters across. And then this distance here, when it's dropping, oh, it's actually going to be like this. It's actually going to go into, it's going to go a bit lower, right? A bit lower. I don't know. I think that looks about right to me. A deck is shown, yeah. I'm just checking I got everything. Determine the required length of the davit arms. There's a clearance of this much between the ship's side and the lifeboat at launching. And it has a 10 degrees, so you're going to drop it in the water. Oh, I guess it's going to be lower down. That's it. There we go. This wasn't quite making sense. That's better. So we're going to drop it in the water like that. It's not going to be completely flat on the ground, but this distance here, that's the one I'm looking for. That's going to be, this little bit here has to be 0.8 meters. Now we're talking. That has to be 0.8. Oh, I can see a triangle here. Look at this. Let's see if we can just pick that out by itself and just work on that. How can I put it like this? Sorry to move around so much. All right, cool. This is forming a triangle here. I don't know if you can see that. Let me copy and paste this thing so I can pull it apart. I'll put my original up here. It's fine, I guess. What I'm trying to show you is... I want to make an original so I can break it apart. This is going to make a right angle triangle here. Look at this. Let's get nice and big so you can see it. It's going to make a right angle triangle. I'll do it in blue, like this bit here. That's what I'm trying to get. That's my objective. And I know how long the base is on that because they tell me in the original question how long it is. They say it's 2.1 meters on the deck. So this is 2.1 meters. And then I know this is 0.8. And I know this is going to be 1 meter more because the lifeboat is 2 meters across. So it must be half a meter here. So I can put all that stuff together and we can draw just that triangle by itself. And we can say this is going to be a really hard question. This is going to be 2.1 plus 0.8 plus 1, which is 2.1 plus 0.8 plus 1. That's equal to the 3.9 meters. Great. So the whole thing has to be 3.9 meters and this angle here has to be 10 degrees. And then they're basically asking how long is the hypotenuse? How long is this davit arm? Now, is that all I have to do? Is that the whole calculation? Let's have a look. 10 degrees, determine the required length. Why did they give me this setup to start with? Why? Why did they tell me this is 75 degrees? I don't know how long that is. I don't know how long this piece of string is here. The thing is just going to swing over and hopefully not smash into the corner of the deck at any point. There's nothing else I can do with this. I don't have the information to do anything else. I'm just checking it. Determine the length. There's nothing else I can do. 0.8 meters. So I think that's it. I think I can just jump into it and try it. Hopefully it doesn't break the ship. So the lifeboat. Okay, so basically this is what we're going to calculate is the hypotenuse of that. I'm going to use Rotor to do it. Let me just make a bit more space, scoot this over to the side, because I already know. Let's do Rotor. I'm going to draw a little guy here so I can get my opposite. This will be my adjacent. This will be my hypotenuse. Okay, and I want to know my hypotenuse, so I'm going to write down, let's see, some old hippie caught another hippie tripping on acid. A good way to remember it. Alright, let's have a look. I got the hypotenuse, which is good, and I got the adjacent, which is all of this. So hypotenuse and adjacent, that's going to be cosine. So let's write down the formula for cosine. Cosine is going to be cosine of the angle is equal to adjacent over the hypotenuse. I know the values, I can just plug these guys in. Is going to be cosine of 10 degrees is equal to the adjacent, which is 3.9 over that hypotenuse, which I don't know. Now I'm going to multiply 3 by x, divide 3 by cosine. Effectively, I'm just going to swap them out. I'm going to flip these guys. Because the x is equal to 3.9 over cosine of 10. Okay, that gets me my x value really quickly. Let's see if it's any good. 3.9 divided by cosine of 10. Now if you want me to go through that in more detail, let me know. I'll totally do it. We got 3.96. So x is equal to 3.96. It's not much bigger. It's not much bigger than the required length. It's going to be, yeah, I mean, oh, okay. So yeah, it's going to be hanging just there. That actually makes a lot of sense. 3.96 meters. I think that's good. Really tough question. Only 6 marks? No way. That is so hard to do for 6 marks. Right, we'll try the next one. Okay, we're going to try question number 3. This is a really, really hard question. I'm not really looking forward to it. But we'll give it a go anyway. Right, I determined the area of the shaded region and given these angles. They told me that this angle was pi over 3 radians. Now, it's 9 points. It's totally worth doing. There's a couple of things we need to know about this. Like pi over 3 radians. I guess we're not really used to thinking in radians, so we can write degree and then radians. We need to know one bit of information about degree and radians, which is in a full circle of 360 degrees, there are 2 pi radians. So I can keep cutting this up. I can cut it in half. What's half of 360 will be 180. And what's half of 2 pi will just be 1 pi radian. And then I can do that again. I'm actually going to cut it into pi over 3. So I want to divide this. Like here I divided by 2. And I did that on both sides. So then I'm going to divide this by 3 to turn it into pi over 3. Now 180 divided by 3 is going to give me 60 degrees. So that's really good. That means that this is equal to 60 degrees. The reason why I want that is because I can think easily in 60 degrees. Degrees and radians are just 2 different languages, and it's like trying to learn a second language. You tend to think in your primary language, your first language, and then trying to learn a second one is a little bit difficult. So I'm going to keep thinking in degrees. Same thing for the 2 pi over 3. How do I get to 2 pi over 3? Well, that's just the same thing, just times by 2. So I can multiply this by 2 as well to get to 120. I did actually divide this one by 3. I didn't write down. There we go. So now I can say this is equal to 120. So saying this angle is 120. This is 60. And then I'm trying to think if there's anything else I can get from that. Yeah, I think so. I mean, let me just draw this shape out again, nice and big, so we can see it. Well, that's about the same. Let me swap these guys around. Let me pop this down here. Don't really need it up there anymore. Somewhere we can see it. And then I'm going to draw a big circle. This thing is a radius. This thing is also a radius. So they tell me the radius is equal to 5. This is equal to 5. This is equal to 5 centimeters. That's great. And then these guys are here. I'm trying to work out, are these the same? Is this the same as that? Is it just like a diamond shape, like a rhombus or something? Not sure. Probably think it is, but I don't know if it actually tells me in the picture. I remember last time I did this, I couldn't do it because it didn't give me enough information, I'm pretty sure. But anyway, this is 60 degrees is 120 degrees. 60 degrees is pretty special because it means that it's like a equilateral triangle, which means they're all exactly the same. I think it looks like that. I think if I cut this exactly in half, I think there's definitely a way to do it. Then we can say that this guy right here, that'll also be 60 degrees. And then you know the internal angles of a triangle all up to 180. So 60 plus 60. So this must also be 60 degrees. So I think this is just all made from equilateral triangles. Which if it is, it's pretty nice. And what are they asking for? They're asking for the shaded region. So I'm just trying to find the shaded region, the area of these 2 triangles. Well, that means I can actually take out one of those triangles. And we can look at them like this. There's a couple of ways we can do this, but I'm going to do it by cutting up into two right angle triangles like this. And then I should be able to use Sokotoa to work this out. I need to know the height, because the area of a triangle is the base times by the height divided by 2. So I know the base of this thing is 5, because they're all 5. All the sides are the same because all the angles are the same. So they're all 60, 60, 60, and the base of this will be 5. But I don't know the height of it. I know the hypotenuse will be 5. We're going to get into a right angle. This is going to be 60 degrees as well. And then I can just use Sokotoa on this triangle here, on this little triangle here. I'll draw it separately so you can see it. Let me just scoot this up. So I'm going to do Sokotoa on this little triangle here. Let's see if we can do that. Just this guy here. So let's pull that out to the side. Like this. So this is going to be 60. This is going to be 2.5 on the base because obviously we cut it in half. It's 5 on the hypotenuse. Oh, I don't even need Sokotoa. I can just do Pythagoras. We can just do 5 squared. And we're going to do a squared plus b squared is equal to c squared. And I've got c squared, right? So I can rearrange this into like a squared is equal to c squared minus b squared. And then square root it. So that's exactly what we're going to do to find the height of this thing. We can do 5 squared minus 2.5 squared, and that'll give me a squared. Let me grab my calculator, and I'll pop that in. 5 squared minus 2.5 squared. Where's my 0.5? 2.5 squared. There we go. I got like 18.75, and I'm going to square root it to get the height. It is this number, 4.3333. So we'll say 4.33. I'm going to use the exact value of my calculator, but I'm just going to write it down like this. It looks like it's centimeters, which is really good. Remember, base times by height is going to give me, base times by height divided by 2 is going to give me the area of this thing. And then I'm going to need, well, 1, 2 to make a whole triangle, but then I need 2 more. So, well, 1, 2, 3, 4. So let's just do that. Base times by height. So this is the height. Times it by the base, which is the 2.5. Divide it by 2. Don't have to divide it by 2, but we'll do it anyway. This is 5.4. So this triangle has an area of 5.41. 5.41. Yeah. And then I'm going to use 4 of them because there's 1, 2, 3, 4 of them. So let's times it by 4. 21.65. Well, that's pretty good. 21.65. The answer then is going to be 21.65 centimeters squared. That's for that area. Not that bad this time. Managed to get through it. Hopefully it's alright. Okay, let's have a look at question number 4. This says we got to plot the following graph, the data on a graph. Pretty simple, pretty easy to plot a graph. We just got to be careful that we don't shoot ourselves in the foot by choosing the wrong number of squares to do this, these numbers here. I'm going to have a look at those first of all. The x-axis does not look like a problem. I really want to spread it out and make it as big as possible. That'll allow me to get an accurate answer. Determine expression. Okay, allow me to get an accurate answer for if I have to use the graph to get any answers. It doesn't look like I do actually have to do it on this one. I could use it for part C, but I just want to make sure this is accurately drawn with this 5.8, 0.4, 0.6, 0.2, negative 0.2. So it has to go up in 0.2s. Look like the maximum value I want to go up to is 6. The minimum value I want to go down to is 1.2, so I don't know, we can make it 1.4 or even all the way down to 2. If I set that as the max as 6 and the min as negative 2, it has to go over 8 and it has to have the 0.2 things in it. So I'm just going to jump into that. We're going to just try it. 6, 5, 4, 3, 2, 1, 0, negative 1, negative 2. That'll actually work really nicely. If I start here, 6, 5, 4, 3, 2, 1, negative 1, negative 2, that'll look even better. So I'm going to start here with 6, this is 5. The reason why I'm choosing this is because I've got 5 little squares, and every little square will be 0.2. So if I zoom in on this, I kind of started at 6, which is kind of weird. I guess I didn't want to run off the top of the page. So this is 4, this is 3, this is 2, this is 1, this is 0, this is negative 1, this is negative 2. Oh, I made a mistake because I have to get the x-axis on either side. So these numbers want to be right in the middle. Luckily on my computer I can do this. Real life is going to be a bit harder to move these things around, obviously. And then I want to have negative 1, negative 2, 1, 2, and 3. Oh, that's really good. I got really lucky. Yeah, these are a bit of a pain. We have to redraw them all again. It's so much work. Ugh. Okay, so that looks good. Just to be clear about this, the reason why I've got this amazingly drawn line, that's just not on the x-axis. The reason why I got this is because this is going to be 0.2, this is going to be 0.4, this is going to be 0.6, this is going to be 0.8, and that's going to be 1. And I can really check that. I really want to make sure. I don't want to have to redraw this thing. I've seen a lot of wonky graphs, a lot of bad graphs in my time. So I know it sounds easy, but it's been a long time since you guys have done it. Just make sure you can plan it out first of all. Okay, and then we have to do negative 1 on the x-axis, negative 2 on the x-axis, 0, and then 1, 2, and 3. Oh yeah, I'm saying x-axis. Obviously the x-axis goes left and right, and the y-axis goes up and down, just to be sure about that. Right, now, if I get it in the center of the screen again, we can just plot these guys up. So let's give it a go. I'm going to start at 0, 3 because it's easy. I'm not going to start at the first point because it's a little bit harder. 1, 1.6. So that'd be 1, 1, 1.2, 1.3, 4, 1.6 right here. And then, so then that is 2, 2, 0.2, nice. It looks like it's going to be a straight line actually. 2, 0.2, we got that one. 3, negative 1.2, so this will be negative 1.2. Cool, and by now I think I can just draw a straight line through it and it'll tell me where the other points would be. That looks really good. In real life, I get my ruler and line my ruler on it. I can get a ruler. Don't really need one, I don't think. And then negative 1, 4.4, so that will be 4, 4.2, 4.4 right there. It does say I should plot them, so I'm plotting every single one. Negative 2 is 5.8 is right there. And then it doesn't say this, but I'm going to draw a line through them using a ruler. I'm not going to extend it any longer because it doesn't say I should. It doesn't say you should go further. I don't think you'll get marked down if you did continue that line off on both sides, but I'm just trying to follow the rules, follow the instructions. Okay, that was basically A, done. Now we're going to do B, determine expression. This is a bit more work, it's a bit different, right? So how do you find an expression? Expression is going to be like y is equal to mx plus c, where m is the gradient or the slope of that line. Is gradient in British English and slope in American English. So the slope is basically rise over run, and I can pick 2 points on the graph and count how many squares. So that's the easiest way to do it. I can do the calculation. You can do the calculation for m, which is y2 minus y1 over x2 minus x1. You can do it that way. Or it's the same as saying, this is actually saying the rise, the change in the y over the run. And since I got a picture of this, I can just use it. I'm going to zoom in a bit so I can see it clearer. When I talk about rise over run, I'm really talking about this will be the rise, how much does it go up by, and then this will be the run, how much it goes along by. Let me just neaten that up a little bit. So let's have a look at the rise, how much is it going up by? Well, in this case, it's not going up, it's actually going down. It's going from 3 down to 1.6. So that must be negative 1.4. It's actually going down by 1.4. And it's going across by 1. So it will be negative 1.4 over 1, which is the same as negative 1.4. This is the rise of a run. This is the slope or the gradient. So that's also my m value right here. So let's put it back in the center of the screen. Okay. So then my m value is equal to negative 1.4. The c value is the intercept. It's where it crosses the y-axis. And you can see really clearly it's just 3. It's actually given as 0, 3. So again, you can do a calculation on that, but you don't need to. And you won't have to on these tests either. So c is equal to 3. And just put it all together. So you got y is equal to negative 1.4x plus 3. This will be my final answer for part B. For part C, they say determine the value of y when x is equal to 1.5. I can plug it into my equation, or I can get it from my graph. My 1.5 is a bit difficult to get off my graph because it's halfway between these values. So seeing as I got a calculator, I'm just going to use it on my calculator. So I'm going to say y is equal to negative 1.4 times by 1.5 plus 3. And that will give you a nice clear answer. 1.5 times by negative 1.4 and then add 3 onto that. And it gave me 0.9 as an answer. 0.9. So that's it. That's the value. I can check out my graph. I should be able to draw a line up to here and across. And you can see it'll come out as about, like if I draw on, it comes out about 0.9, but it's not very accurate on this graph because I didn't build the graph to do that. But we got the equation, so it's okay. Okay, let's try question number 5. We got a concrete beam as this shape, and we're going to get the volume and the surface area. Now this is a composite shape. It's made from a box on the bottom and half a cylinder on top. So we're basically going to break it down and draw it like that. I'm going to make this a little bit smaller so I got a bit more space to draw it. We're going to do the box on the bottom, I suppose, first. It's pretty simple. That'll be the easiest one to do. Let's just draw a box, cuboid shape. I call that box. Volume, that's pretty easy. Let's break it down to 2 shapes and do them side by side because I'm gonna have to do the volume of this thing, and then I'm gonna have to do the surface area. I'll do the surface area underneath it, and the top shape is gonna be a half a circle And then these lengths are going to be basically the same. Well, that's pretty bad drawing, but whatever, it'll do. Now let's have a look at these things. How big are they? That says that the radius is 20 centimeters. If the radius is 20 centimeters across, it means the diameter is going to be, let me write down 20 centimeters. It means that the whole length will be 40 centimeters. That is the length of our box. So this will be 40 centimeters on the width. And then let's see how tall the box is. It's going to be 30 going upwards. That's nice, 30 centimeters. I just forgot to check the actual question. Are we meant to be working in centimeters or cubic meters? It doesn't say, it just says volume of the beam. We can do it in anything, so we might as well do it all in centimeters, no point in messing around. And then the last thing is to write down 120 centimeters on the length. Let's get everything in frame. Let's hold it right there. So 120 on the length. All right, that looks good. We got all the dimensions on the box. And I think we got all the dimensions we need for the cylinder. Oh yeah, the half cylinder. It's going to be 120 centimeters long. And it should be a bit more like curvy. It's pretty bad drawing. Let's see if I can fix that a little bit. Yeah, it's still pretty bad. Whatever. I don't need the diameter actually. I just need the radius. And then I need to remember my formulas. What are the formulas for the volume? So let's talk about volume. This is really easy. It's just width times by length times by height. And let's see, that's going to be what? 30 times by 40 times by 120 or thereabouts. I might have mixed that up a little bit. I can multiply them together in a second. Let's do the volume for the cylinder. It's going to be the cross-sectional area for any cylinder. It's always I would call that the base times by the height. The base in this case is half a circle, so a circle is pi r squared. Let's see, pi r squared, but then it's divided by 2 because it's only half of one, and the height is okay. That's good. I know the height is 120. I'm going to call this the height. So the pi r squared that's 20 centimeters. So it's going to be pi times by 20 squared over 2 times by 120 for my calculation. That looks about right. Let's just scoot that up a bit so we can keep it all in shot. And get my calculator. And we'll just crack that through. So 30 times by 40 times by 120 for the volume of the box. Really easy. 144,144,000. Double check that. Yep, centimeters cubed. Easy. And then this guy, let's do this square part first because of PEMDAS, BODMAS. So we do the exponents first. Square that. Times it by pi. Might as well. Here it is. Divided by 2. Here equals. Times it by 120. Here equals. Get as a decimal. 73.398. 73.398. I think I made a mistake there. 75, yes, 75. 39.8. 0.22. Nah, that would be fine. Centimeters cubed. So of course the combined volume of those two things together, the total volume would be this plus this. Let's just add them together. I've already got this number in my calculator. To add the next one's pretty easy. We're going to get this 2193.98. 2193.98. That's a 9. Centimeters cubed. As long as you write the units, it should be fine. That's great. Let's just double check that last number. 2193.98. Perfect. Now we're going to do the surface. I can't spell it at all. Surface area. Now the surface area is actually a lot more difficult. I think I'm going to pull this aside and do a whole nother calculation for it, because there's quite a lot of stuff going on here. So let's do that. Let's grab those pictures, drag them off to the side, and then we'll talk about surface area over here. We need a couple of things for surface area, a couple of formulas. Let's get the formulas first of all. So let's try and get it all in shot and keep it like that. Okay, so surface area is gonna be for the box. The top side is not connected. It's connected, so you can't see it. So this we have to exclude this top bit. We're not going to include it. But the trick to this is breaking it down and just doing it step by step. Obviously, this is a 3D box, so it has. That's a really terrible drawing because you can't see the extra leg on that. It's a 3D box, so it has another side. Another side we can't see on this. So anyway, I'm going to do let's call this the front and let's call this the back. So I'm going to do the front plus the back. And the trick about this is getting everything nice and organized. So the front and the back. The front is just going to be 40 times by 30 centimeters squared because it's just a rectangle. And then there's front and the back of them. So we're going to times the whole thing by 2 like that. Then let's do the left side. I'll call this one the left side. And there'll be a right side. That'll be exactly the same. That's still good. So we call this the left plus the right side. And again, it's going to be a rectangle. So it's going to be 120 times by 30. Nice and easy. But there's 2 of them, of course, because we've got left and right. Now we're going to do just the base. There is no top exposed because it's covered by this half cylinder lid. So we'll just call it base. And the base is a rectangle. It's going to be 40 times by 120. 120 times by 40. Great. Now we can calculate all those and add them all up and get a total for it. I'll do that in a second. I'm going to do my half cylinder top to it now. The cylinder is a bit more complicated. It's got a front side here, and then it's got this curved top to it, this curved roof on top of it. So let's do the front and the back. The front and the back are half circles. Actually, the 2 half circles come together to make a full circle, so I just need pi r squared to calculate what that is. And then I already know what r is, it's 20, so that's it. That's all we need. This will be front and back. Front and back. I didn't write back, so let's put front plus back. Is going to be pi r squared. So that's going to be pi times by 20 squared. That's it. That's all I need. And then the curved surface area. Now this is a bit more tricky. A curved surface area of a cylinder has its own little formula. We're actually going to use half a radius. Let's just go for the formula. I'll teach you how to do this in another video. We'll go through this in more detail. But for now, we're just doing exam run through, so not too much detail on it. I'm just going to use the formula straight up. It's the circumference of the circle. So the circumference of a circle, this is a curved surface area. And the circumference of that circle is going to be pi d. So it's going to be pi d. And then we're going to times it by the height, the length of it, which is h, pi dh. But because it's only half of it, we're going to divide that by 2. Which is great. We know all those values. We can just say pi times by the diameter will be double this, so it'll be 40 times by the height, which is 120. Divide that by 2. Everything divided by 2. That's it. Let's just crunch all these numbers through and see what we get, and we add them all up. So I'm going to do the trickiest ones first. Let's do pi times by 40 times by 120, and then divide that by 2. It's going to give me this number of 7539.8. 7539.8. Right on the edge there, sorry about that. And then we're going to do we should do a few more decimal places. Let's do that, a few more decimal places on there. It was 0.22. All right. Then we're going to do this one. Let's do the curved surface area. It's going to be pi times by 20 squared. All right, that's 1256.6. 1256.6, and then a couple more, 37. That'd be grand. Okay, all of these guys I'm going to do in one go because I don't want to have to type it in a whole bunch of times. So we're just going to do 40 times by 30 times by 2. Feel free to write this out, but I'm going to just keep going with this. So plus, I can even write it as it is on my page with brackets or parentheses around it, so it looks exactly the same. The reason why I'm doing this is kind of to avoid actual typos. I know that plus will take care of it because of BODMAS or PEMDAS. It will separate these things out and it won't mix it all up. But please feel free to do it slowly and do it separately. It'll be exactly the same answer, hopefully. Times by 2 plus 120 times by 40. All right, 1440. 14400. The reason why I do that is not because I'm lazy, well it is because I'm lazy, but also it's because I really can see everything in one go and I can scroll through it and find any errors. If I have 3 separate calculations, it's very likely one of them's a typo. So okay, great, we got this number, this one and this one. Now we just add them all together. Let's get 1440. We'll do 1256.637. Check that, looks good. Add on the last one, which is 7539.822. Put them all together and we get this as a total. Total is 2319.6. Total of the whole thing is 2319.6. Yeah, 0.4, so that's fine. Centimeters squared, because we're talking about surface area. So that was part B. That's it. That's the answer. We got it. Let's just go back and check the question. It says the total surface area of the beam. Yes, we got it. We do not need the base of that half cylinder, right? There is another base, but it's stuck on the top. So it's good. We got everything. We got the volume of the beam as well. All right. Next question. Alright, question 6 is just some fractions. Everyone loves fractions, right? So let's have a look at these guys. We have to show all of our working. We can do this on a calculator, but it doesn't say show all your working. So I could actually do it all on a calculator. I'll show you how to do that, because you probably guys don't know how to find the things in the calculator to actually do this. 2 and 6/7 can be written on the calculator like this. There's some special buttons here. We got some fraction buttons. It's a little bit different in each calculator. This one actually has an actual fraction button. So I can just write it as being 2 and then 6/7. And then you can see I could just type in the rest of it. It's divided by 3 and then the fraction button. Whoops. Okay, a bit of navigating is required. 3 and then 2/3. Okay, so you can see I can just type it all in here, but you know, that's no good. I mean, what is good, I can definitely check my answer in an exam. That would be really useful. Your calculator probably has like an ABC button, and you can do the same thing. It doesn't write it quite as nicely. It'll write it a bit weirder. This on a calculator will look like 2, and then when you press the ABC button, it gives you this thing, and you got 6, and you got this thing again, and a 7, and that means 2 wholes and 6/7 as a fraction. It's a bit clunky. But we should really know how to do it by hand anyway. This is going to be useful for higher level algebra later on. So let's write this out and do it properly anyway. We'll use the calculator as a crutch now and then, and we can always like test things and check things on the calculator anyway. So it's worth doing. Alright, so these are mixed numbers. We're going to put them into top heavy fractions. I think we're going to put them into top heavy fractions. Actually, there's a couple of ways to do this. If I'm adding these guys together, then I can add the whole numbers, so I get 5, and then I can just do 2/3 plus 4/5. There's a couple of ways to do this. I'll show you 2 or 3 different ways every time we do a video. I'm going to do it this way this time. I'll do it another way a different time. So I'm now going to add together these 2 fractions. In order to add those fractions together, I need to have them common denominators, so we just need to cross multiply them. So we're going to times this one by 5, times this one by 3, and we're going to get, what's that, 10 plus 12. So I write it out. It's going to be 5. And this will be 10 plus 12 over 15 over 15. The 10 plus 12. Let's get rid of that whole number. This is going to be equal to 22 over 15, which is equal to, how many 15 is going to 22? It's 1 with a remainder of 7 over 15. And I need to add that back onto my other whole number, which is a 5. So this whole thing can be written as 6 and 7/15. That is the internal part here. Oh, that's great, but I could have kept it as a top-heavy fraction. I should have just done that to start with. Oh, well, like I said, a couple of ways to do it. So far we've got 2 and 6/7 divided by. Now to do the divide, I really do need it to be a top-heavy fraction. I kind of tried to avoid doing that, but now I'm going to have to do that anyway. How many is, oh, let's just do it on a calculator. 6 times by 15. I'm sorry, I'm covering it up. The reason why I'm doing 6 times by 15 is to pop it into a top heavy fraction. 6 times by 15 is 90, plus the 7 is going to be 97 over 15. That's great. Divide, and then 2 times by 7 is 14. 14 plus the 6 is 20, so 20 over 7. Now we're going to divide these 2 fractions. We're going to use keep, flip, change to do that. So we're going to use keep, flip, change, which means we keep the first one the same, so it stays as 20 over 7. We flip the second one, so it becomes 15 over 97. Oh, that's so ugly. And then we change this into a multiplication. And 20 times by 15, 20 times by 15 is equal to 300. And then 7 times by 97, wow, 7 times by 97 is equal to 679. 679. This is so ugly. Is it right? I don't know if it's right. I probably made a mistake. Divide it and see if it simplifies. It doesn't simplify. Wow, that's ugly. Let's see if I made a mistake. Let's just check it all through. Checking these guys. Add up to make a 5. 5 times 2. Yeah, that's a 10. Yeah, 3 times that's a 12. 22. And that's a 7. And then that's a 1. And then 6 times that. Yeah, probably. Well, looks right, but it doesn't feel right. It feels like I made a mistake, but whatever. We'll go on to part B. Part B. Let's do another color. Part B is 3 and 1/6 minus 2 and 2/5 times by 1 and 2/3 and 2/3. All right, let's get to work on this one. Let's put all this into top-heavy fractions or improper fractions. So 2 times by 5 is 10, plus the 2 is a 12. So 12 over 5 times by 1 times by 3 is 3, plus that is a 5. 5 over 3. This is really nice because it means I can actually cancel this out. I can simplify this whole thing, or I can just do it on my calculator. It doesn't really matter. And, well, you might as well just cancel this out. It gives me literally 12 over 3, which is equal to 4. But I can do it on my calculator. I can say 12 divided by 5. That's this number. And times it by 5 divided by 3. I put it in brackets or parentheses. And it comes out as 4. So it checks out. So now I've got 3 and 1/6 minus 4. That's pretty easy to do. I could do it in my head. I could tell the answer is going to be 5 over 6 because negative 5 over 6. It could be negative 5 over 6. Ooh. Yeah, because I can do 3 minus 4. Well, almost. I can break it up. I can just different ways to do this. I'm going to have to show you how to do this in a nice, easy way because I'm using all different techniques all over the place. I could write this as 3 and 1/6 minus 3 minus 1. That's what the negative 4 is. Oh my goodness, that's so confusing. This is going to be 1/6 after these guys cancel each other out. Minus 1, that's where I get the 5/6 from. But we should do it in a nice, easy, slow way. But I'll do it next time. I'm so sorry. Okay, so we got 5/6 for the first one. And we got 300 over 679 for the part A. Next question. Okay, this is question 7. It's part B, it's section B, which is switching from mathematics into mechanics and physics. So it's going to be a little bit different. Number 7, a turbine rotor has a diameter of this much and rotates it that much. Okay, turbine rotor. Well, I guess that means it's a spinning circle. Let's see. It has a diameter of, let's draw a picture of it, a diameter of 0.6 meters. That's great. And then it rotates at this many radians per second. Rotates. I mean, that's like a rotational velocity. So I guess I could call it U as an initial speed. It'd be 400. I could just write down speed or something. 400 rads per second. Rad per second. Okay. The linear velocity of a point on the rim. Okay, let's have a look at what that means. Linear velocity. Let's scoot this guy over a little bit. I don't need anything else about this. What's happening is this object, this is a spinning disc. It's a spinning turbine. And then there's a point on here that the whole thing is spinning around. So it'll spin around like this. And we can calculate the speed at which that blue dot is going around at. I mean, basically what they're asking for the linear velocity is if this blue dot flew off and, well, maybe it hit you in the face. Then the question is, how fast is it going when it did hit you in the face? So, I mean, that would be useful to actually calculate if you're working on some machinery and it goes wrong. Then you want to see how fast this thing is going to hit you. Yeah, well, pretty fast probably. So let's calculate it. Linear velocity, and we can use SUVAT, linear velocity of a point on the rim. Or we can use a SUVAT equation. Actually, linear velocity, isn't that just speed? And can't we just say speed is equal to distance divided by time? I mean, we can do something a little bit different, but can't we just do this? because we know it does 400 rads per second, and we know the diameter of the disk. So what I'm trying to say is that we can work out how far this thing travels every second, and then that will be a linear velocity. We better get it in meters per second. Because if it's spinning around like 400 or 500 revolutions, or like I don't know, like 50 revolutions or 100 revolutions per second, then we can work out the distance traveled in that 1 second, and that gives us the speed. So I need to know the distance. The distance is going to be the circumference. Kind of the circumference. It's going to be 400 radians. How many revolutions is that? We can turn the 400 radians into revolutions. Or I can work out how many times it'll go around the circle in that. Oh, we can do how many times it goes around the circle. You know, in a full circle, there's 2 pi radians, which is about 6. If I take my calculator and times it by pi, it's like, there's like 6.28 radians in a circle. So if we're doing 400 radians, can I not just divide the 400 by this? Let's try that. And that should tell me how many full revolutions I've done. So 400 divided by 2 pi. It comes out as 63 revolutions. Maybe that's useful. I don't know. 63.66 revolutions. 16. We'll call that revolutions now. So first thing I did, I convert into revolutions. Maybe it's not the best way to do it, but it's the way I'm doing it right now. Then how far is that to travel? How far does it take to go all the way around like that? What's the distance? The distance would be the circumference of that circle, and the circumference of that circle would be given by, we'll call it circumference of the circle is pi d. I already know what d is, so I can say this is equal to pi times by 0.6. We can calculate that as pi times by 0.6, and we get, well, 1.8849, etc. This is 1.8849 and then like 555 meters. That's how long the distance this thing is traveling. And it's doing that 63 times every second. So we can times it by 63.6619 to find that the total distance traveled every second. You can see it's 19.9999, which is basically 120 meters. So let's just call that 120 meters. This is the distance traveled in 1 second, which happens to be the speed or the velocity, because we can say the velocity is distance divided by time. So we can say the same thing as speed, basically. It's going to be 120 meters divided by 1 second. This is meters, this is 1 second. So we say the velocity is 120 meters per second, which is exactly what they're asking for, of a point on the rim. That's great. We got that one. I'm doing it this way to make it easy for you to understand, or doing it this way so we can understand it. There are different ways to explain it, and I get a lot of people saying that their teachers in school or colleges explain it in a really completely different way, and it doesn't make any sense. So in my tutoring classes, we break it down, look at it different ways, and eventually we find a way that you will understand. So if you don't get it this way, don't worry. I can explain it lots of different ways until we find one that you do like. So rotational, let's do it part B. The rotational speed of the turbine motor in revs per minute. That looks really easy. It looks like we've already calculated this. The rotational speed of the turbine in revs per minute. Let me just pop that up there. Rotational speed of the turbine in revs per minute. Looks like we've already got a lot of information in order to do that. We already have the number of revolutions per second. Rotational speed and revs per min. So if this means we do revs per second, we do 63.6619 revolutions every second, then how do I turn that into minutes? Well, it's going to be 60 seconds in a minute. So I think if I times that by 60, it will turn it into revs per minute. I mean, if you travel this much distance in 1 second, then I do that in 60 seconds, that's the same as 1 minute. So it's a really easy question once I get to this point. Because of how I've broken it down, I don't have to go and get anything else, I already have it. Times it by 60, what's that? 3819.7. 3819.7 revolutions per minute. Great, that was part B. That was easy. And then part C is the number of radians turned when the turbine rotates through 325 degrees. That's very easy as well. We're just going to use one piece of information to do this. Now, radians are a bit annoying because it's like another language. We're not used to speaking it. It does make a lot of sense when you're doing stuff like traveling over the surface of a curved object like the Earth. And when you're traveling from here to here, then you're not traveling in a straight line. Even though every time we do a map, we pretend we travel in straight lines, we don't really do that. We travel across the arc unless the Earth is flat, and then we do go in straight lines. So basically any kind of movement you do on the planet Earth, assuming that planet Earth is not flat and it is a sphere, then you need to use a lot of arc calculations, which is exactly where radians are used. So that's why it's good to have them. But for us right now, they're just a bit annoying. We need to know one piece of information. In degrees is 360 degrees is a full circle, and a radian is 2 pi radians. It's about 6 point something radians. Right, so then how do I turn it into 325? 325. You know what would be easiest if I just turned it into 1 degree and then multiplied that, because I can turn this by dividing it by 360. And then I can turn it into 325 by timesing it by 325. And as long as I do that to both sides exactly the same, we should have the same result. This is like a ratio. So let's see if we can pop that in there. Divide that by 360 times by 325. In fact, this is applying a formula, but I don't remember formulas very well, so I'm remembering a process. And the cool thing about this process is that it's really universal. It works for just about everything. Formulas tend to only work for one thing. Depends on how your brain works or how you think your brain works. So let's go 2 pi divided by 360. And then we times that by 325. And put it into like a decimal version. So 5.67. 5.6723. Radians in, that's how many radians it turns through when it goes through. So it's 5.6723 radians is equal to 325 degrees. That's it. That's the answer. Super simple, nice and easy. Next one. Okay, we're going to try question number 8. A pump on a water main discharges through a pipe of 100 millimeter diameter against the head, right? So it's a pump and it's pumping water. Let's see if we can understand what's going on. We got a pipe and it's pumping to a head of 32 meters, which means there's a pipe pumping upwards and it's lifting water to, well, if I could draw it like this, this is a circular pipe, but it's going to be lifting it 32 meters up in the air. Well, up. And I mean, you know, this is for pumping out tanks, cleaning out the ship, I guess, pumping out the ship, bilge pumps or whatever. So you've got 32 meters, a constant velocity of this thing. You can ignore the effects of friction, the pump and pipe work. That's nice. So what we're going to be doing is effectively we're going to be lifting a big chunk of water, this whole pipe full of water. Imagine it was a solid cylinder. So let's make it look like a solid cylinder. Something a bit like this. It doesn't look very solid actually. But imagine it was a cylinder like this and we were lifting it up. This is what the pump is effectively doing. We'll see this with the other questions when we're doing like cranes or we're lifting loads. Imagine you were lifting this whole pipe full of water. It's 32 meters long, but how wide is it? How much volume is it in there? How much volume is inside of this thing? Let's see, it's 100 millimeter diameter. So let's work on that pipe. We've got 100 millimeter, which is the diameter. I really need the radius of this thing. That says 100 meters. That's not good. 100 millimeters is the diameter. And I want to get the radius. So that means it'll be 50 millimeters on the radius. I'm going to have to make this a little bit smaller so I can fit it all on. Okay, so we got 50 millimeters on the radius. I need everything to be in meters. So let me grab my calculator and we're going to convert this into meters by dividing by 1,000, right? So 50 divided by 1,000, just because I don't want to make any mistakes on that. I've got 0.05. So 0.05 meters is now my radius. The volume of this cylinder, which is the pipe, is going to be pi r squared times by h, because it's a cross-sectional area of a circle and then the height of the thing. So we can just plug this in now. I think we got pi 0.05 is the radius, square that, times it by 32, which is going to be the length of it, and we can get a volume of this thing in meters cubed. I want the volume to be in meters cubed because all the rest of the calculations will be in meters cubed. So let me go grab my calculator. There's my radius. We can square it, and then I can times it by pi, and then I can times it by, what was I had to timesing it by? By 32. All right, so I get this number. Let's see. I'm going to say the volume is equal to 0.25132. All right, meters cubed. That'll do nicely. Now, in order to get the weight of it, the mass of it, the mass will be the volume times by density. It's like the size of the thing times by how heavy it is. So the volume times by density, right? You can think about like how big this thing is and times by how much it weighs. If it was like polystyrene or styrofoam, it'd be really light. It doesn't matter how big the thing, it'll be super light. But what it's going to be pretty heavy, it's going to be a kilogram per liter, right? Per liter. This thing's a meter cube, so 1,000 liters. Anyway, let's plug it in. 0.251327. That's the volume times by the density, which is in kilograms per meter cubed. It's salt water, so it's a little bit heavier. So we just times this guy by 1025. All right. So we get 257. This is 257 kilograms, 0.61 kg. That's really good. So this is the weight of the thing, the mass of the thing. We got to work out the power of the pump. Oh, I didn't list any of my equations or anything. Let me just scoot this down to the side. I can go down there. Now, this is the weight of that water that we're going to be lifting up. Now, we've got to talk a little bit about work and power. Work, well, you all know what hard work is, hopefully. It's like pushing a heavy object is hard work, right? And the longer you push it, the harder it is, the more work you do. So imagine you're pushing a car and you push it like a little bit, that's okay, but pushing for a long distance is more work. Actually, work is exactly equal to energy. Like the more work you do, the more energy you use. So work is actually something like force times by distance. And that's exactly what's going on here. We're applying a force to lift this thing over a distance. It's a little bit more specific in this situation. But let's talk about power while we're here. Power, what's the difference between like a not powerful machine and a very powerful machine? What's the difference between a powerful car and a not powerful car? It gets you from A to B. For example, a car will get you from A to B. A slow car or a not very powerful car will get you there slowly, and a faster car will get you there, well, a more powerful machine will get you there quicker. It does the same amount of work, it just does it in a different amount of time. You can think of that like as a powerful computer will do the job quicker than a not powerful computer. So power is really work over time. It's something to do with work and something to do with time. So the formula is just work over time. So now we're getting some. We can start putting this all together. We've got force times by distance over time. The actual force that we need to apply to this thing is going to be the mass times by gravity. So we can have mass times by gravity. The distance is actually going to be the height we're lifting this thing divided by time. So now we got our power equation, which is power is equal to mass times gravity times height divided by t. It's like mugd. I remember it as mugd. It sounds like miles per hour, so it's like mgh instead of mph. So I can remember that quite easily. But what are we going to be? How far are we lifting this thing? And the really weird thing is, it depends on the question you're doing. But this one they give us as a velocity of 3.5. You know, velocity is like speed. It's distance divided by time. So we have a distance and time in here. It's like tagged in there. So this h over t is the speed, right? So we've actually got everything we need in here. This is 3.5. I can literally swap out that blue bit for this 3.5. We're going to plug it all together. Right, let's change colors so it will mix together. So now we're going to say power is equal to the mass, which is the 257.61 kilograms, gravity, which is 9.81, the height of this thing over time is actually we are lifting this 3.5 meters every second. 3.5, that's the time. I mean, it literally is over 1 second, so it's okay. Imagine, like, literally as the water's coming in here and it's coming out again at 3 meters, 3.5 meters every second. It doesn't matter if we were physically lifting this tube up in the air at that speed, like this, or if we were putting a chunk of water in and then taking it out the top. The effect is equivalent. Anyway, let's calculate this and see what we get. So we've already got this number in our calculator. We're just going to times that by 9.81, times that by 3.5, and cross our fingers and hope for the best. We got 8845. The power is equal to 8845. What do you measure power in? Yeah, we measure it in watts, right? Watts. So I write some more digits on here for accuracy. 986, okay, 99. This will be in watts. We can drop it into kilowatts if you like. So the power of this pump is going to be 8.8451 kilowatts. Great, that is the power of the pump. That's question A done. Part B says the motor to drive the pump if the combined electrical and mechanical efficiency is 88%. Let's might have to do it off to the side and make some more space. Let's have a look. We're going to look at efficiency. What is efficiency? It's quite a simple calculation, really. Let's see. I got to drag it off to the side. Let's go over here. All right. So we're going to look at part B. The efficiency of this thing, which means that the way I think about efficiency, the problem is there's a lot of different types of efficiency for different calculations. Generally, efficiency is, I can't spell efficiency. Efficiency, I was trying to hide that because I can't spell to save my life. Okay, efficiency is going to be like the theoretical power required to do that job divided by the actual power required to do that job. What's going to happen is we just calculate the theoretical power as being like this 8.8 kilowatts. So it's going to be, scoot this down so we got some more room. It's going to be 8.8 kilowatts. What was the rest of that number? 8.845 kilowatts. But when you measure it in real life, it doesn't actually cost this much. It costs a bit more because we have to lose energy. We're going to lose energy through the mechanical efficiency and friction and the heat from the motor. Like, no system can be 100% efficient, and definitely no system can be more than 100% efficient. So the way we can remember this to check if we got it right is that the big number should be on the bottom and then the smaller number should be on the top. But oh, I forgot to do this. We're going to times it by 100 because it comes out as a percentage. We'll do that in a sec. The actual power is the one I'm trying to calculate. The motor drive the pump is combined. Yeah, the actual power is this one. And it's going to be 88%. So I guess, I could just write it as being 0.88. That's 88% as a decimal, right? So all I'd have to do is solve this equation. We get it. Like I said, it's pretty easy. We can just literally flip these guys. We can divide through by the 0.88 and multiply through by x. I'm not going to do that on the page because it makes the calculation look really messy. And we're going to be doing a lot of these, just flipping things over like this. So it's a nice shortcut. 88. I'll explain it again later in more detail if you want to see it, how I do that. We can just flip it. So let's give it a go. We're going to take this number, divide it by 0.88. That's it. 10. So the answer is going to be, what is that? 10,051 watts. Or I guess we could say that's 10.051 kilowatts. This is the actual power required to the pump. It's a nice, easy little end to it. It's worth 3 points, but it's always the same, this little twist at the end. It's pretty simple. That's it. Next one. Okay, we're going to do question 9, which is a uniform beam. I really like doing these. These are really complicated if you do them the long way. And we managed to work out a nice, neat little table to keep everything under control. There's some basic concepts we need to talk about, but yeah, we'll go over them as we go. I think you'll see how it all comes together. what we're going to be doing is we've got an 800 kilogram beam. There's loads of weights on it. Okay, that's fine. The method we're going to be using can just accommodate as many weights as you need to. So they can do 5 weights, no problem. And then we want to know the reaction forces. So how much of these fulcrums, these pivots here, pushing back up. And what we're going to do to understand what's really going on here is imagine you were, this is the pivot. We're going to be pivoting about here. And imagine you're like a little guy, you're going to come around here and you're going to lift it up. We're going to lift this beam up. And oh, let me lock that down. And we're gonna lift it up, not from the edge because we're not lifting from there. We're gonna lift right from here because that's where the fulcrum is. And imagine you're doing this with a table in real life, right? So what you do is you walk around to the table and you just lift the edge up. You can gauge how heavy the thing is, or how much force is required to lift it up. Or really, you're gauging how much force this fulcrum, this support here is under. You don't want it to crumble and break, so you can lift it up. And you can do the same thing on the other side. We can walk around the other side of the table and we can lift it up this side. It's probably more likely to be heavier one side than the other. But we got a nice little trick on this to speed things up. We're just going to lift it up from this side. So I'll leave my little guy there so I can see what's going on. We are literally going to be taking pivots at A. So we can write that down as pivots at A. I'll tell you what, I'll write it up here. Which means we're taking moments about A. This is really, in technical speak, it should be moments about A. Which means I'm lifting at B. All right. Then what we're going to do is name all of these weights, because we've got 250 grams, 250 kilograms, we'll call that weight 1. We've got 500 grams, we'll call it 500 kilograms, we'll call it weight 2. And then we've got this 1,000 kilograms, we'll call it weight 3. Then there's the beam somewhere. We've got a beam of 800 kilograms. It's going to be right in the middle of this beam. So I'll put it on there and I'll just label it up as is. I mean, normally I'd draw a diagram of this myself, but seeing as I got a diagram here, it's not that bad. I'll just use it. We got 800 kg. All right. Now we've got everything nicely labeled up. We're going to build a table. So the table goes like this. We're going to write down the names of the objects. Let's see if I can, I don't want it too low on the video. So all right, scoot up a bit. We've got names. Then we're going to have the mass. These are the masses of those 250 kilograms. They're really the masses, not weights, but whatever. Then we're going to convert those into forces, because anytime you do any work with mass, you generally have to do it under gravity. So we're going to times it by 9.81 to turn into forces. We've got forces. Then we want the distance from the pivot. So we write down distance. Then we want the distance. Oh, this is going to create the moments, because force times by distance is equal to moments. We can write it up here. We've got force times by distance is equal to moments. There's a couple of like little concepts we're dealing with in the table, and they just all kind of pile into one. They just like one goes into the next one, goes into the next one, which is really nice. We've got moments. Then I really care about if these are anti-clockwise, so anti or clockwise. We really want to know what direction these things are going in, because we have to do at the end, we have to do the anti-clockwise moments have to be equal to the clockwise moments. Otherwise, this thing would be flying around all over the place. Clockwise moments. So it's not spinning around, it's all in equilibrium. So this is the equilibrium conditions. So let's just build up the table. That'll do. So write down some names. What are these things called? Oh yeah, we call them weight 1, weight 2, weight 3. There's a beam in there, and then there's also the reaction at B, this guy lifting it. I want to know how much force he's using to get that in there. Okay, I hope that all fits on there. Then we're going to say the mass. What's the mass of this? It's 250 kilograms. We can do this whole thing in tons, or we can do it in kilograms. It really depends on the question. This one is in kilograms, so I'm going to do everything in kilograms. 250, 500 kilograms, weight 3. That's meant to be a 3. Let's scoot up a bit so you can see a bit clearer. Weight 3 is going to be, what's that, 1,000 kilograms. And then the beam is 800 kilograms. And the reaction force, we don't know, we don't care. It's not really a mass, it's just a force. So the force will be in newtons. And we're going to times each of these by 9.81 to get it into newtons. So 250 times by 9.81. 2452. 2452.5. And then the next one will be, well, 500 times by that. So that's actually going to be 500 times by 9.81. I was going to double it, but we'll keep it nice and easy. 4905. 4905. Next one is 1,000 times by 9.81. Pretty easy. 9.81 is 9810. I'm doing it all on my calculator because I don't want to mess it up. So there's no point trusting my mental arithmetic right now. 7848 newtons. Nice. And then the reaction force, I'm going to call X because I'm looking for that. I can still use it. I'm just going to label it up. Now we have to take the distances from the pivot, right? So this is the pivot. Oh, this is one of the most difficult things to find. Like, can you work out all these distances? That looks like it's a meter away because we go 3 meters this way, 2 meters this way. So I'm going to call it 1 meter. All the distances are going to be in meters. How far is weight 2 from that? Well, it's 7 plus this 1. Like I said, you want to spend some time on it. This is the trickiest bit. This is going to be 1 meter here. So that's 7 plus 1, so it's going to be 8 meters. Weight 3 is way over here. What is that going to be? That's 2 meters from the edge. This thing is really long. How long is it? 4, 10, 2. Oh man, like what's this going to be? It's going to be, the total beam is 4 plus 10 plus 2, 16. And it's 2 away from that side, 2 away from that side. So I think I can just minus 4 from it and we get 12. So I think it's 12 meters away. I think this whole distance is 12 meters away. You really want to spend some time working these out. I'm kind of doing it kind of quickly. The beam is, the weight of the beam is this, we always take a load as being as a point mass. So I'm modeling this as exactly in the middle, the center of gravity of this thing. We just worked out the beam is 16 meters long. So this must be 8 meters from the edge. This will be 8 meters here. And then I want to go 2 meters back again. So I'm going to call it 6 meters. And then this guy lifting it is exactly 10 meters. It tells me that is nice. All right. So in order to get the moments, we multiplied these things across because force times distance equal to moments. So we just multiply them. Oh, that's easy. That's going to be 2, 4, 5, 2.5. The moments, if you want to know the units, are going to be in Newton meters. So let's put them in there. Newton meters, right? Multiply the next one across. That's going to be 490. That's not an 05 times by 8 is equal to 3924. 3924.0. And we go to the next one. 9810 times by 12. 117720. Quite big numbers, but we can handle it, no problem. 6 times by 78, 48. 47088. And 10x on this last one because we're just going to multiply them across. We don't know what that is, but we're going to call it 10x. Right, now is it anti-clockwise or clockwise? All right, here's the grand finale on this really. So we're going to see what direction these things are working in. This weight, if they could pivot freely about the pivot, which way would they swing? That's the kind of thing that's going on in my head. So this one would go this way. The beam would also go that way. This weight would also go that way. And then this one would as well. We ignore this is not a pivot right now. It's a lifting. You know, this guy wasn't here. He just drops it. The whole thing would just fly this way. So these are all clockwise. So clockwise, 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 clockwise. And the only thing that's anti-clockwise, poor guy, is this guy trying to lift it like that. So this guy's anti-clockwise. And we're going to use anti-clockwise moments are equal to clockwise moments to solve. So let's pull that off to the side because I think I need a little bit more space to have a look at that. Let's just grab this and try and solve it over here. Will it all fit in? It's quite big, isn't it? I'm not sure it's going to fit. Let's grab all of my, let's see if I can squeeze it in here. We're going to have, there's a lot of them. So we're going to have, let's grab this. I think it will fit down here. Anti-clockwise moments and then equal to clockwise moments. I'm going to change my size on that one. So I'm just trying to get it to fit on the screen. So we're going to go clockwise. I'm going to say all this in the exam because it's communication. It's good communication with the examiner to show you understand what you know what you're talking about. So I'm stating little laws of physics, little facts. So clockwise moments should equal to, it's really the sum of the clockwise moments. to the anti-clockwise moments. We don't need this anymore, I don't think. And then I'm just going to add up all of these. So I can write them down. It might take a while. So let's just add up all these clockwise ones here and write down the number carefully. 2, 4, 2, 5. Probably make a mistake on this. So double check your numbers. All my students I work with, they're always tripping up over their calculations. Well, almost all of them. And it's just normal. You're not used to using calculators so much. 088. All right. So really double check all your numbers and stuff. I'm not doing it right now. I'm just going to trust that's right. 2064. 2064. 73.5. 73.5 Newton meters, right? And then my anti-clockwise, well, that's equal to 10x. And now we just got to solve that for x. Can we solve it for x? Sure we can. We divide by 10. It's super easy. We can cross that out. So let's get this undivided by 10. This tells me we get 20. Well, it's the same thing, just minus the 10, isn't it? So screw that down a bit. So 7.35 Newton meters is equal to x. And this is the force required to lift at that point here, right? So that is the reaction force done. It just tells you straight the answer. And this way of building a table is quite adaptable to different situations. You can change out the force. If you know the force, you need to calculate the distance. It's pretty much the same thing. It's really adaptable. It's really nice. So this is the reaction force at B. Now we're going to use a nice, neat little trick to get the reaction force at A. We know that the total downwards force, down force, must be equal to total up force, upwards force. Otherwise, this thing will be flying around all over the place. It will be moving. It's not. It's in equilibrium. It's just static. So like all these things pushing down here, all these weights pushing down must be in balance with those fulcrums or those supports pushing up. So we've got all of them except from A. So we can do a really nice little shortcut on there. So total forces down. Oh, I get it from my table. Here are my forces right here. Sorry to move around so much. Here are my forces. I've just worked out what X is. So I'm just going to grab them and drop them down here so we can see them a bit better. And then this has to be equal to, well, the one I just got, I put it in Newton meters. This is wrong. I'm so sorry. It's just newtons. It's just a force. This is the reaction force at B. So let me write this a little bit better instead of just having numbers all over the place. 1 second. Just move this across. Move this across. We're going to add up all these numbers. But what are these numbers? This is basically the weight 1, weight 2, weight 3, and then the beam. And this is going to be equal to the reaction force of A plus the reaction force at B. That makes it easier for the examiner to see what you're doing. I would really suggest writing this as neatly as possible and clearly as possible. I read a lot of the examination notes and they say that they couldn't understand what the students were trying to do. The people taking the exam were trying to explain. They couldn't follow their work. So now we've got total down force equal to total up force. And all we're going to calculate is this RA. I might as well just call it RA at this point. We're going to add up all these newtons minus these newtons off from it. And then we should get this guy by himself. So I'm going to add up all these first of all. They're slightly different numbers from before. So we've got 24, 52.5 plus 49.05 plus, again, checking my typing. I'm going to make a lot of typos. Be really careful about that. Plus 78.48. What do we get? 25,000. Yeah, look at that. I'm going to go minus 20. And then I'm going to minus this number off from it. So minus the 2647.5. To get 4,000. So that should be my reaction force. I just literally did this minus this. So let me just write that down so the guy can see it. 25.01. 5.5 newtons minus the 2647.35 should be equal to my reaction force at A, and that's equal to 43.68. 43.68 newtons. So it looks like the reaction force at A is a lot less than reaction force at B. Let's see if that makes sense. What's going on in this beam? Yeah, I mean, like he's got 1,000 kilograms behind him, 500 kilograms of under him. So he's taking the brunt of the force is on B, and only a little bit is on A. That's a bit like a wheelbarrow, like lifting one end of the wheelbarrow. A's got the lighter D on that. But that's it. We got everything we needed to. We got the reaction forces. So that, okay, on to the next one. Okay, question 10. It looks like a Suvat equation, I think, or it's a friction equation, maybe. Let's have a look. Stationary block with mass 150 kilograms has a force applied to it which causes acceleration on the plane. Looks like an easy one. It looks like we've done all the hard ones in this test. There's going to be hard questions and easy questions, and they're quite spread out. They're quite evenly distributed most of the time. Sometimes you get some couple of really hard ones together. A stationary block with a mass of 150 kilograms. So there's my block with 150 kilograms. Has a force applied to it. I'm not going to read the whole thing. It's too much information for my brain to handle. So has a force applied to it which causes an acceleration on a horizontal plane. Okay, great. The force is this much. The force of 1,778 newtons is applied at an angle 10 degrees below the horizontal, pulling the block. Why would you do that? Why would you do it why would you pull it down like this? This is really not a good way to pull a block because we're adding to the friction force. Some of this diagonal force that we're pulling down with is actually pushing the block into the ground, which is causing more friction. It'd be much better if they were lifting it like this because that would actually alleviate some of the friction. But whatever, I'm not the boss. All right, so this is 10 degrees going down like that. And we've got, what is it, 1770 newtons on that angle down there. All right. Yeah, I don't really see it anymore. Let's just make it so you can see it clearly. There we go. Nice. 10 degrees. Okay, nice. Determine the acceleration of the block if the coefficient of friction is 0.2. Coefficient of friction, that's mu. We'll put it up here, 0.2. We're going to be using it in a second. There's going to be quite a lot of backwards and forth on this. We've got to break this down into its horizontal and vertical components. So I can literally take this triangle. This is my force triangle. I'll copy it over. And we're going to look at it in two sections. We're going to look at the horizontal elements of this and the vertical elements of it. The horizontal is going to be the part that's pushing the block. And the vertical part is going to be the part that's pushing the block down into the ground. And in this case, adding to the normal force, because obviously this thing has a weight as well. It has a weight to it, which is pulling it into the ground because of gravity. And these two forces combined, these two red forces I'm drawing on, are going to be contributing to the friction, which we'll get to in a second. So let's break this down into its two respective horizontal and vertical forces. Let's call the horizontal X because the X direction is horizontal. Let's call the vertical Y because that's vertical, right? So let's solve for X. Solve for X, and then later we're going to solve for Y. It's going to be basically the same thing. We're going to use Sokotora to solve for this. This little triangle is going to be, well, let me draw a little guy here so I can understand what I'm doing. This is going to be my opposite to him. This will be my adjacent to him. And this will be my hypotenuse to him. Now we need silly old Harry caught a lot of haddock trawling off Africa. So we need Sokotora in order to do this. We have the hypotenuse, and to solve for X, we need the adjacent. So it's going to be my Ka. So let's go ahead and write that down. We're going to use Ka, which means cosine of the angle is equal to the adjacent over the hypotenuse. We can plug the values into this one. Let's zoom out a bit, get a bit more space. We can plug the values into this. This is going to be cosine of that angle, which is 10, is equal to the adjacent, which is the X, over the hypotenuse, which is this 1770. In order to solve for X, we just multiply both sides by the 1770. So I get 1770 cosine of 10 is equal to my X value. And that's really nice. It's really easy, really clean. It's always like that. It's always the same. We're constantly breaking diagonal forces into the X and Y elements. Okay, now we're going to do the same thing. Before I calculate this on my calculator, I'm going to do exactly the same thing for my Y because it's so easy to get set up. The Y is the opposite, and I've got the hypotenuse. So opposite hypotenuse, I'm going to use the So. So let's write it down as So. This means sine of the angle is equal to the opposite, which in this case is I'll write down the actual formula. Opposite over the hypotenuse. And this is going to be sine of the 10 is equal to the opposite, which is y, over the 1770. Again, same trick as this, same treatment. We're going to multiply both sides by 1770 to get sine 10 like that. That's equal to y. Right, now I got my calculator and actually calculate these guys. They're going to be pretty easy to calculate. Let's do it over here. So 17, whoops, that's not 17. 1770 cosine. Make sure I'm in degrees, not in radians. Otherwise it won't come out right. Let's see, 1743. So x is equal to 1743.1 newtons, right? And then same thing, I can even just backspace this and delete them, put the sign in. I can retype it all, but whatever. 307.35 or 307.36. So y is equal to 307.36 newtons. So this is the vertical that's pushing it down. It's going to be adding on to the force felt by gravity, and it's going to be contributing towards the coefficient of friction. That's actually what we're going to be calculating right now. The horizontal force, the 1743, is what's left over pushing or pulling the block along. And that's hopefully going to accelerate things a little bit. So I could draw that on my picture right now as 1743.1 newtons. We're pushing it that way. Really, pulling it, pushing it, doesn't make any difference. Now let's solve for friction. All right, so let's get a friction formula. I'm going to need this picture, so let me grab it, and we're going to solve this whole thing for friction over here, I think. Right, so let's drag this up. We're going to solve for, let's get this, yeah, that probably looks better, right? Don't want to go too far away from it, you can still see it, but whatever. Okay, so let's solve for friction. Okay, so friction's fun. It's F mu n. And this is really like the downwards force. It's a normal force from the block. But like I said earlier, we've got some downwards force already pushing down it. And the rest of it will be because of gravity. So we can calculate the normal force, which is just the push down on the block, right? Because of gravity. The more gravity we have, or the more block we have, the more push we're going to have. It's just m times by g. It's mass times by gravity. So it's 9.81. times by 150, as we always do to get it into newtons. So it's going to be 9.81 times by 150. All right, so it's 1471.5 newtons. So this is pushing down with a force of 1471.5 newtons. But then we had this little red force over here, which was this. It was the y force. It's 307. So we need to add on the 307.36 newtons as well to get the total force pushing down on it. Like I said, this is not a good way to pull a block because we're making things worse. 307.36 newtons. We're adding to that friction. So now we can calculate the friction force on this, which will be friction. I'm going to call it frick. The problem is there's too many F's and N's, and N is not newtons. In this case, it's normal. There's too many of these letters in physics, and they just get all over the place. So the more you can annotate it, the better. I'm going to call it frick. It's friction force, but whatever. We've got the coefficient of friction. Do you remember over here it was 0.2? So it's going to be 0.2 times by the combination of everything pushing it down. So these guys added together. I should have added them earlier, but whatever. 1471.5 plus the 307.36. All right, this is going to give me the friction force. So I've already got this on my calculator. We can add on the 307.36, and then we times it by that coefficient of 0.32, and it gives us the friction force. This is the resisting force. This is what's stopping us from pushing the block. It's 355.772 newtons. It's stopping us from pushing this block. We're pushing it with this force, and this is the resisting force. It's a bit like the tax we're paying on the whole process. It's not that much. I mean, we're really pulling this thing forward. It's really fast with a lot of force. So I guess I could add it into my picture. I'm going to destroy my picture a little bit now. It's going to be like this. It's going to be 355.772. I don't even care about the downwards force anymore. I'm just going to simplify my picture. Usually in the actual exam, I just have one picture and I just keep adding onto this thing, but I want to kind of keep it simple so you guys can see it. Okay, this is now what's going on. We're pushing it or pulling it with a 1,743 newtons, but then we're resisting. This is resisting. So we want to talk about the net force, like what's left over at the end. So let's talk about the net horizontal force, like the bit that's left over. It's just going to be that 1743.1 minus the 355.772. Let's calculate that. So I've already got my calculator. I can do 1743.1 minus the answer from previous, and I got 1387 is equal to 1387.328. I thought this would be easy. It turns out it's quite long. We're on the last stretch now. Now, in the question, it asks us, determine the acceleration of the block. So in order to find the acceleration, we're going to use F equals ma. All right, so let's do the acceleration of this thing. We're going to use F is equal to ma. We know the block has a mass of 150. We know the force we're pushing it is this one here, so we can work out A from that pretty easily. We're going to say 1387.328 is equal to 150A. Transpose for A, I mean like divide by 150, and we can get A. So get a calculator. I've already got it in my calculator. Divide it by 150. Hit it. 9.24. That is fast. That is a fast acceleration. Right. Normally it's like 2 point something, but 9 is a lot. Acceleration is 9.24. 885. 885. That'll do, won't it? Meters per second squared. All right. That's it. That's the end of that question. Okay, let's have a look at number 12 here. A hoist has a pulley and an axle with the following dimensions. Pulley diameter and axle diameter. So we are going to produce a simple dimension sketch of the lifting machine. We're going to draw it anyway. Even if they didn't ask me to, I'm still going to draw it. So what we're talking about, there's lots of different versions of these. They have them with little different, different combinations. We'll see them in different ways, but they're all pretty much the same kind of thing. They are actually all basically levers. We're talking about a lever, even though it's a circular lever. And what's going on here is we have a pivot in the middle, and we are pulling it on the outside. So you can imagine this like being a lever, and imagine you're pulling it here or lifting it, and you'll be lifting the load right here. It's exactly the same as the moments equations we did earlier. This gives us a mechanical advantage to how much you're pushing it up, and to how much load you can lift. The longer the lever, the more mechanical advantage you have. So what we have here is we have a big wheel and a small wheel. The small wheel is called the axle, and the big wheel outside is the pulley. And we are going to be pulling this thing down. So in order to draw a quick diagram of this thing, I can show that this is the force applied. Force applied as we're pulling it down. I mean, really, in order to explain to you guys, I would draw a little guy here pulling it down, because that's what's going on. And then we are going to be, this is going to rotate, it's going to go in this direction. It's going to rotate the drum this way, and it's going to be lifting up a load, and the load has to be on this side. It definitely has to be on this side. So let's draw a load on it. We can make it a little bit bigger, and we'll call it load. We'll say load. And this is going to be going up. If we put it down, it's going to be going up. We have to draw it on this side. It would not make sense to draw it like this. This would not really help us at all. It would not go in the right direction. It would be coming down as we go down, as we pull. So this is where it's definitely going up. Oh yeah, and what I was trying to say is that this would not really be helping us. This would be in a 1-to-1 ratio, which is not very useful at all. This is actually going to be a different kind of ratio and give us some kind of mechanical advantage. So that is going to be our diagram for part A. Produce. Oh, I need to include the diameters on these. So we'll just do that. We'll just squeeze this across so we have a bit more space. Let's put some diameters on the diagram. Yeah, I think I can remove that. I should be fine. The diameters are going to be for the big wheel. This is going to be 200 millimeters. So I'm just going to use exactly what they have here. Not going to change any units. And then we got the internal diameter here, which should be 50 millimeters. All right, cool. That's it. It looks like I got all the information on that. Really, really good. Force applied, load. Looking good. Now we're going to calculate the movement ratio for part B. Movement ratio then, I don't know if we've done this before, but let's have a look. Movement ratio is what it sounds like. It's how much you move by. It's actually how much you move divided by how much the force moves. I remember these as always being the big number on top and the small number on the bottom. So it's going to be the movement that I make, movement, or the distance, let's call it distance, the distance I travel, divided by the distance the load travels. Okay, so this is true for all of these situations. It's always like this. They have to adapt it for each situation a little bit. In this case, the distance I travel, or the rope I am having to pull, is actually going to be equal to the circumference. If to do one rotation of that wheel, I'd have to do the one circumference of the big wheel. So the circumference is given by pi d, and we've got d here. It's 200 millimeters. So we could say pi big D. Let's scoot it over here. So we can say pi big D divided by the distance the load travels will be on the small wheel. And that would be small d. To give you a better idea of what it looks like this. It'll be pi times by 200, and on the bottom it'll be pi times by 50. And now we can actually just cancel out the pi's in that case, and we can do this calculation of 200 divided by 50. I mean, it's pretty obvious, it's 4, so no need to even do it on the calculator, I suppose. We'll still do it. 200 divided by 50 is going to give us 4. So it's a 4-to-1 ratio. We don't have to write the to 1 bit. It's just kind of like implied that our movement ratio of 4 means 4-to-1. It means it's giving us 4 times mechanical advantage. It means that we can lift, well, we're going to see in a second, I suppose. We can lift a bunch of like 4 times the weight we're applying to this thing. All right, that's the movement ratio. So now we're going to look at part 2, which is the efficiency of the machine. Now the efficiency is, it says the efficiency of the machine is required, the efficiency of the machine, if it requires this much effort to load a mass, to lift a mass of this much. So efficiency is always going to be the big number over the small number. So I can lift, this is the force to lift load. Now, of course, we might not be lifting, we might be pushing, we might be breaking something apart, but I don't care. I'm just going to write it like this because it's simple, it's easy for me to remember. The force to lift load, and then this is the force applied. This is how much I'm pushing it or lifting it. Force applied. And it looks like we've got the force applied. They've given us the force applied as being 400 newtons. So I can put that on the bottom. I'll put 400 newtons on the bottom. And then the force to lift the load, we're lifting 90 kilograms. So 90 kilograms times by 9.81, because we always have to multiply it by gravity in order to get a working force on this thing. So 90 times by 9.81. So we are lifting, the force we're lifting, yes, is going to be 882.9 newtons. 882.9 newtons. And we'll divide that by the 400. You can see it's about 2. Wait a second, that's no good. You can't have over 100% efficiency. So I got this backwards, 400. I got it confused with something else. So I got 2.2. This is not right because we cannot have 100% efficiency. So I'm so sorry, I got these guys backwards. Let's quickly fix that before anyone notices what I did wrong. So yeah, you can't have over 100% efficiency in anything in physics. So I got to flip all these around and we'll put it back how it should be. So let's put this one down like this. That's how I can remember it and how I can fix it if I make a mistake. Hey, we all make mistakes. So let's just flip all these around. Now we're going to times this by 100 at the end as well because we want efficiency to be in terms of percentage. So I can say that the system is 50% efficient, 100% efficient. Well, it can't be 100% efficient. 79% efficient. So this thing looks like it's going to be about 50% efficient. Now that I got the right way around, let's try again. For 400 divided by 882.9 and then times that by 100, 45.3. So we got a 45.3% efficient system, which these numbers really come from measuring. You can't calculate them because of course, we're losing efficiency in the system itself. It's quite a simple system, so we're not losing that much. 45 is not bad. But we're losing quite a lot in friction and friction in the ropes, friction in the chains, in the pulleys, in the axle itself. All right, that's it. We're all done.